Hey, welcome back. So one of the last topics that we're going to talk about with galaxies is the idea of dark matter. You've probably heard of it. It makes up, theoretically, about 95% of all the matter that's in the galaxy, but it's stuff we can't see, we can't touch, we can't taste, we can't smell, we can't interact with it in any way, yet somehow it's there. So we're going to look at the data that shows the evidence for dark matter, and we'll talk about some possibilities for what it actually could be. Keep in mind, though, bottom line, we don't really know what dark matter is, or even if it even exists. So kind of be skeptical as you're watching some of this stuff and think about your own ideas. What do you think could be explaining what we're seeing out there? All right, let's get started. All right, so we're going to be working with dark matter, so make sure you've got your class notes out. That's going to be tool 27. Looks like this. So have that out, and as always, pause the video until you're ready to go. All right, so Kepler's third law governs pretty much all the motions that are occurring in the solar system and in the galaxy and even in the universe. It works really well. Kepler didn't know why it works, but we now know that this is because it's based on gravity. If you have Newton's law of gravity, you can actually derive Kepler's law from that. Kepler just saw the pattern, but we know that it works in reality and it works really well. So let's review some of the things when we're applying this to a galaxy. So A is still the Sima major axis. That's the distance from the center of the galaxy out to whatever particular star we happen to be looking at. P is the orbital period of that star. That's how long it takes it to go around the center of the galaxy. But M has always been the mass inside the orbit. But in the case of the solar system, there's really only one mass in the solar system. The sun makes up, over 99% of all the mass in the solar system. So as I move outward, yeah, I may add a planet or an asteroid in there, but it's like nothing compared to the sun. So it doesn't even show up until I get out to 4 or 5 significant digits. So almost all of that mass is in the sun. As I move outward, it just doesn't change much, the total mass, as we move out. So let's do a sample calculation. Let's look at finding the mass of the sun using Jupiter. So we use m equals a cubed over p squared because I want to find the mass. Remember, I just solved this for p. We've done this, or for m. We've done this before. The Sima major axis of Jupiter is 5.203 AU. The orbital period of Jupiter is 11.86 years. So we're going to plug that in and do it along with me in your calculator. So when I do 5.203 raised to the third power, I get 140.8. And then I'm going to divide that by 11.866 squared, which is also 140.8. And I end up with, hey, look at that. The mass of the sun is 1 solar mass. Well, duh, it's the sun, right? So we expect that. But the technique is the same, no matter what. Now, if m is constant, so I want to keep this number here, m, the same. What happens to p if a increases? Well, if the top number gets bigger and I want the whole fraction to stay the same, well, then that bottom number has to get bigger too. Let's think about that. So if we have an example, let's say that we've got a fraction here and I've got, I don't know, let's say I've got 5/4. All right. If I want, actually, let's make it 4/4 just to make the math easier. Okay, if this goes up to a 5, the bottom number also has to go up to a 5. Otherwise, the total fraction, the mass in this case, is going to change. So if A goes up, P goes up. Do you see why? Okay. So if the orbital period goes up, so let's say that it takes a lot longer to go around the center because the orbital period increased. What does that mean about the orbital speed? If it's taking longer to go around, then the orbital speed must be slower. It must be it's traveling at a lower velocity as it goes around. So when we plot this for the solar system, here's the orbital speed. And you see that Mercury has the highest orbital speed because, well, it's closest to the sun. It takes the least amount of time to go down. And then the orbital speed gets slower and slower and slower as we move out towards Pluto. So the mass inside of all this is basically constant. It's pretty much just the sun. So the orbital speed only depends upon the mass inside the orbit. That's what Kepler's third law says. Now, in the case of a galaxy, though, it's only going to be the mass inside of that star's orbit. So remember that the galaxy is not a thing. It's made up of a whole bunch of things. It's made up of a bunch of stars. It's not orbiting this black hole in the middle. That's not what's making everything orbit. It's actually all of the stars are pulling on it. However, you might say, well, what about the mass of this stuff on the outside? Well, over one orbit, it actually cancels itself out. So if you think about it, this material over here, let's look at this edge. When the sun is over here, it's experiencing a lot less gravity from this point than the sun is experiencing from here, because the sun will be closer. If the sun's where it's drawn here, it's closer here and farther away here. So over time, it will cancel each other out. So all of the mass outside of the orbit of the sun cancels each other out. You don't have to know. So more mass inside of this circle means a faster orbital speed. So as the mass gets bigger, what happens to the orbital period? Let's prove that. So we're going to keep A the same. We're going to keep the distance the same. So say we're at the distance of the sun. If I were to increase the amount of mass inside of that orbit, what then happens to the orbital speed? Well, let's look at it. So A is staying constant. M goes up. P is inversely proportional, so it has to go down. Well, if the period goes down, the period gets smaller, that means it's going around faster, right? Doesn't take it as long to go around. If it's going around faster, then it's got a higher orbital speed. Let's go through that one more time. So A is staying the same. A is constant. M goes up. Because M's in the top and P's in the bottom, P must go down. Well, a shorter orbital period means it takes less time to go around the center, and so therefore it must be moving faster. So as we plot the speeds of these things, as we move out from the galactic center here, we find that once we're in the bulge, we get increasing speed. Well, remember that if I just had the sun, for example, that speed would decrease. So that means we're adding mass. Well, that makes sense. It's the bulge. There's lots of stars in there. So as I move outward from the center, I'm adding more and more stars inside of the orbit of the star that I'm testing. So the orbital speed goes up quite a bit. When I get to the edge of the bulge, and before I hit the first spiral arm, there's very little material in there. So it's just like with the solar system. So all of the mass is the bulge now, but as I move away, I'm not adding any mass, so my speed goes down. When we hit the first spiral arm, now I'm starting to increase mass again. Well, you guys know that if I increase the mass, then the orbital is going to make things whip around faster, so the orbital speed is going to go up. So these stars that I'm testing at the edge of the first spiral arm, as I move through the spiral arm, their orbital speeds are actually going to increase because there's more mass. That the mass that's being added from the spiral arm is being added to what's inside. So once I leave the spiral arm, now I've got most of the mass is already inside, so I'm not adding more mass, so my velocity goes down. And notice that this allows us to determine where the sun actually is. This bump, this is the bulge here, this is the first spiral arm, so the sun is on the outer edge of the first spiral arm, and sure enough we are. So that falls off in the space in between the arms because we're not adding any mass. As soon as I hit the second arm, though, I'm starting to add more mass inside of my orbit. And so that means the orbital speeds start to increase again. Now here's where something gets weird. There are only 2 spiral arms in our galaxy, but then as soon as I move past that last spiral arm, well, now I'm not adding any more mass. So Kepler would predict that the speed should be falling off, just like it does in the solar system. Think about it. All the mass of the galaxy, I'm out at the edge of the galaxy now, all that mass is inside the galaxy, and I'm not adding any more stars. There are no more stars out there for it to add. So it's just like having all the mass in the solar system. So all the speeds then should taper off just like we see in the solar system. Here's the problem. It doesn't. And so when we actually measure the speed of any gas and dust that's out there, it's moving way too fast. Remember, the only way that this could be higher than what Kepler predicts is if I actually add mass. So the amount of mass that I'm adding must also be increasing, because here I'm just adding a little bit, here I'm adding more and more and more and more, until out here I'm adding a whole lot. So this is the only evidence for dark matter. So there are no stars here, yet there's some sort of mass that's making the gas and dust move faster out at the edge of the galaxy. We can't see it, again, we can't touch it, doesn't interact with any kind of matter. We have no idea what this stuff is, but this is called a flat rotation curve, and we see this in essentially every galaxy. The dark matter increases in such a way that it exactly cancels out that Keplerian fall off and stays pretty flat. Why that would be true, we don't know, nor do we have any idea what this stuff could be made out of. So let's look at some candidates. Well, one possibility is stellar mass black holes. So we're not talking about the supermassive black holes in the center of our galaxy. We're talking about, normal black holes that have formed from type 2 supernovas, that sort of thing. All these things, remember, are really, really rare because there are very few 20 solar mass plus stars out there that could even become a black hole. And there's no way that this could make up 95% of the galaxy, because if we look at how much mass we need to keep that curve flat, it ends up being that the visible matter that we see is really only about 5% of everything that's out there. So most of the galaxy that you see, all these pictures I've been showing you, is like less than nothing of what the real galaxy is, because the real galaxy seems to be this dark matter stuff. So another possibility is that it could be brown dwarfs, white dwarfs, or faint red dwarfs, stars that we can't really see when they're out at the edge of a galaxy. Well, we can't with our ground-based telescopes, but the Hubble Space Telescope can. So here is a globular cluster that it's looking at that's out at the edge of the galaxy. And looking at this blow-up part, we can see all of the white dwarfs and the red dwarfs, and there's just not enough of them to equal 95% of the mass that should be there in the galaxy. So another thing that's been proposed are weakly interacting massive particles, also called WIMPs. These are some hypothetical subatomic particle that we've never seen. We don't really have any idea what it is, but weakly interacting means that it doesn't interact with matter other than through gravity. That's it. This is massive, which means that it's got gravity, but nothing else. What that could be, I don't know, nor does anybody else. We don't really have any kind of idea for what this could be. It's just been proposed as well. Maybe it's just something we can't see yet. Another possibility, and one that is, I think, a little more intriguing, is the idea that it's new physics, that we just don't have our physics wrong. Every time we have created some mythical substance, we've always had our physics wrong. The last time this happened was, we used to think that light, because it's a wave, has to travel through something. And so we invented this stuff called the luminiferous ether, that was the medium that permeated through space that light was able to travel through. Well, they did a test and they were able to prove that this ether didn't work. And that directly led to Einstein's theory of relativity. So the answer in that case was, we just didn't have our physics right. And this has happened over and over and over. So all of the arguments, like we say here, are based on Kepler's third law. That's, if you don't have Kepler's third law, then you don't assume that there is dark matter, because it's that fall off that makes it how it should work. So Kepler's third law works in our local neighborhood, but what if it's incomplete? So, and the idea is, we know that physics is different when I have lots of mass, because then I get general relativity and black holes and things like that. Physics is different when I'm moving very fast. That's when I get the time dilation effects that we talked about, the special relativity. Physics is different when it's very small. That's quantum mechanics. So maybe physics is different on the scale of things that are very, very large. So maybe, at solar system size, the difference between the true physics and what we're measuring is so small that we just can't see it. But by the time you add that up over the distance of galaxies, now it becomes important. So I am one of the minority of astronomers who doesn't buy dark matter. I mean, my BS flag goes up when I see this. I think we are missing an opportunity here to see if maybe we just don't understand all of the physics that are there, and galaxies could be a laboratory for learning this new physics. Some people have come up with some models that do work, but again, as I said, they're not terribly satisfying, because they don't really make any predictions. They just kind of explain what we've seen before. And well, a model that doesn't make any predictions can't really be tested with that. So the bottom line is, nobody knows. We still don't know what dark matter is, or if it even is a thing. And it's only going to take more time and study for us to find that. All right, so download the dark matter practice sheet. And you'll find that it's here. We're basically doing the same types of stuff that we did here in the lecture. We're going to have you calculate the amount of mass inside the sun's orbit, for example. So you can figure out how much stellar mass there is inside of our orbit from there. All right? So I want to caution you that I am way in the minority of astronomers who doesn't buy dark matter. Now there are more and more people are kind of coming around to that because everything we're trying to do to explain dark matter seems to be failing miserably. But you should understand that, well over 90% of astronomers out there will buy dark matter and think that, okay, well, we just don't know the properties of this dark matter, but we've got some evidence that it's there. If you accept our current models of physics, absolutely, there's evidence for it being there. The question then comes, should we actually accept our models of physics? And well, that's where the new work comes in. Maybe you'll be the one to solve it. We'll see you next time.